So hopefully you've had a go at doing these inverse hyperbolic functions and their graphs. Let's start with y equals sine x. So this looks like this. So if we're reflecting this in the line y equals x, that's reflected in this line. So our function for the inverse, which is seen like this. This is also seen. It can be written like this, or it can be written like this. You can put the c in or not. People can use both. Let's go with the first one. Then this will look something. So this bit reflected is going to look like this, and this bit reflected is going to look like this. So that would be our graph of y equals r sine x. So the inverse, or you can write it like this. Okay, it looks something like this. As x gets bigger, it's going to keep getting bigger. Same with y, but it's this reflection in the line y equals x. For the inverse cosh, this is slightly different in that, unlike sine x, this is actually a many to one, so many values of x. So for example, these two values give the same value of y across there. So this needs to be, we need to restrict the domain so that it's a one-to-one function. So we're only going to consider the domain as a line y equals x. We're only going to consider the domain of this, not like sine x where it was all real values, and you kind of get all real values. Sine looks like this, so you kind of get all real values for both. Here we're going to restrict our domain, so we're only going to go from, we're not going to consider that left hand part, we're only going to consider there for y equals cosh x, and therefore y equals the inverse cosh is going to look something like this. Again, not quite as curved at the bottom as some graphs, so it's kind of flatter, and then it kind of goes out like this. Okay, and this is y equals r cosh x, or cosh minus 1x, and this is for x must be greater than or equal to 1 here. Okay, I must specify that because if I put the other old function back in, that's the bit where it's 1-to-1. When you reach negative x values, it becomes many to 1. So we're going to limit. We've got to limit the values we're looking at, and that limits the domain of this particular function. So here you could argue that y or f of x is also greater than or equal to 0 because we're only interested in positive y values. It's more the domain we're interested in. And then if we look at arctan, or tanh minus 1x, in a similar fashion, you should have drawn this for your graph of tanh with asymptotes of 1 and minus 1 when you were looking at that. So when we do this is, so if I'm looking at the inverse function, that's a reflection of the line y equals x. Again, it's 1-to-1, so that's all fine, but you should have got the domain and range flip for the inverse functions. So the asymptotes, instead of being at 1 and minus 1, y equals 1 and minus 1, then now at x is 1 and x is minus 1. So you end up with something that looks a little bit like this. For our arctan, sorry, and then this is for x between 1 and minus 1. It won't reach those values, or you can write this as mod x less than 1 if you wanted to instead. So that's what you should have got for these inverse functions. That's what their graphs look like. Reflections of the original function in the lines y equals x. These two are more common at the start, but we can also do the r tanh one as well. Sorry, that should have a minus 1 there. Okay, a couple more things we're going to look at with hyperbolic functions. We're going to look at how we can express them in terms of natural logs. So rather than just writing this or this, we can write this in terms of logs, just like we can write sine x in terms of exponentials, this one. Because of that, I can write the inverse in terms of logs rather than exponentials. So let's have a look at how we do this. So we're going to let y be the function. And again, you can call it this, or you can put the -1 in the function. So let y be that. We're going to take sine of both sides. So we take sine of the left, and if we take sine of the right, it cancels out that side. And then we can replace the left-hand side with the identity that we know, but in terms of y. So this will become e to the y minus e to the minus y over 2. And then if we're trying to write sine x, we're trying to get y by itself now, and then we can substitute in and find out what y equals. So let's multiply by 2. I'm going to write e to the minus y as 1 over e to the y at the same time. So I've just times up by 2 both sides to cancel the 2 on the left. And then I've written e to the minus y as 1 over e to the y. Times up by e to the y, like we've done previously. So we get 2x times e to the y on the right. And then gather everything on one side. And this is like e to the y squared, 2x e to the y minus 1. And this time, rather than trying to factorize or use the formula, we're going to complete the square on this expression. A little bit funny because we've got this 2x here, but again, we've got sort of quadratic in e to the y here. So I can think of this as e to the y. In fact, I shouldn't need big brackets. E to the y minus x in here. If I square that, then I'll square the first term, which gives me e to the y squared. Times them together is minus x e to the y and double it, so minus 2x e to the y, that gives me this bit, but then I'm going to have to minus that extra x squared I'd get in, that I always get with completing the square, the last term squared I always have to take away. So I get this, and then from here I can add x squared and add 1. I can square root both sides. Little bit ugly, get plus or minus root x squared plus 1, and then I can add x to both sides. I'm nearly there, but there's a couple of things I've got to take into consideration when I'm doing this. So I need to get y by itself. Remember, y is r sine, or sine minus 1x. So we started with. So if I take the natural log of both sides here, I'll get the y to drop out, and I'll get sine inverse to drop out of this. Okay, but we've got to be careful with our inverse functions because remember, if we take natural log of both sides here, so log of the left, I'll get just y, and log of the right, I'll get log of all this. But I just have to be careful to make sure that I'm not taking log of a negative number. So taking log of a negative is because we know that y equals log x has a domain of x bigger than 0. So I need to make sure whatever I'm putting in, this thing here, needs to be positive. And if we consider x minus root of x squared plus 1, then we should be able to see that this is always going to be negative. So this will always be negative because root of x squared is x. So root of x squared plus 1, x squared plus 1 will be bigger than x squared. So this must be therefore be bigger than x. Rooting something that's 1 bigger is going to give you something slightly bigger than the square root of x squared. And therefore, on that, this means I'm taking x minus something here. This thing here will be bigger than x, won't it? Okay, because this root of x squared plus 1 will be bigger than x. And therefore, y can be log of x plus the root of x squared plus 1 only, and y is my inverse sine. So then I get this as I need to. Okay, that's how I prove Shine. So remember, you can pause the video at any stage you want. This first question is in your booklet. It's proving that inverse Shine of x is equal to log x plus x squared plus 1. So that's the question in your notes that you should be able to find. And then we're going to do the same for the inverse cosh, and I'll leave inverse tan for you to have a go at yourselves. So let's have a look at two, very, very similar. So we want to show the inverse of cosh is equal to log of x plus root, this time it's x squared minus 1 under here. And this is for x greater than or equal to 1. So first of all, let y be inverse cosh. Cosh both sides to get rid of that inverse, and then we can use our identity and then rearrange to get y by itself. Times up by 2, and I'm going to write e to the minus y as 1 over e to the y again. Times up by e to the y. Everything on one side. Sorry, that's my phone if you could hear it. So e to the y squared, get this on the other side. And then again, complete the square. So we're going to have minus x in here again. E to the y squared, there's the first term. Times them together and double it. Second term, we're going to have to minus x squared again, though this time it's a plus 1. Get all of that on one side. So we can square root. So we end up with x squared minus 1. Again, this is a bit of the difference here between this and the one above. Square root both sides. So again, plus or minus the square root of x squared minus 1. And then add x to both sides. And again, we should consider whether or not these things are feasible, because we know we're going to be taking the log of both sides. So we'll get this. This time it's a little bit more fiddly, because x plus this, and remember we're looking at x, we want x to show this for x greater than or equal to 1, but this is always going to be positive, and so is this, because x squared minus, if x squared, if the square root of this is x, then the square root of this is going to be smaller than x, isn't it? Because I've already taken one off before I'm square rooting, so it must be smaller. So therefore x minus it will still stay positive, and obviously x plus this square root is also going to be positive as well. So they are both positive. So that's okay. But if x is greater than 1, then this one is going to be less than 1. Okay, so although it's positive, it's going to be less than 1, because if x is greater than 1, this becomes something like bigger than 1. I'm taking away something which is going to give me something that's negative here, and therefore this is going to not be positive. So the value of this is going to be negative, because if we take something, the log of something less than 1, it will end up being a negative. Remember, your graph of log x looks like this. There's 1. So if I'm taking log of a value between here and here, it ends up being a negative, which we can't have. So we want this. So y, which is inverse cosh, is equal to log of x plus root of x squared minus 1. And this is for x bigger than or equal to 1, because for 1 is fine, because if I put 1 in here, I'll get log of 1, which is 0, which is fine. But if x is less than 1, it won't work, because if x is less than 1, then I can't have this in this question. And I shall leave this one, the proof of this one, up to you.